Uh, okay, so actually, most of the talk won't be about that. This will be at the very end, maybe. Um, but this is joint work with Takashi Ikeda, Shinsuke Iwao, Thomas Lamb, and well, parts of it are collaborations with some of those people. Okay, and thanks to the organizers for um, getting us all together and giving me the pleasure of speaking. So this is the overall outline of the talk. So the overall theme is quantum equals affine. So quantum cohomology, equivariant. You can get all those structure constants are the same set of structure constants as for small torus equivariant homology of the affine Grassmannian. And this works in all types. So you can put your favorite, Liz picture up there, and it works in that type also. And in this quantum equals affine world, there's the quantum side and the affine side, and both of these, the cohomology and homology rings can be constructed by coordinate rings of varieties. And I'll describe both of those constructions briefly, and also on the one bonus from going over to the homology of the affine Grassmannian is that because the affine Grassmannian is secretly a loop space, you get a Hopf-algebra structure on its equivariant cohomology, and so the homology and the cohomology form this pair of Hopf-algebras that are dual to each other. So you get all this extra structure, so I'll talk about 3 realizations of this homology of affine Grassmannian, and I couldn't resist. I stuck in matrix affine Schubert varieties just because I couldn't help it when I heard things that are going on here. I just thought I'd stick that in there. One slide that you can make K-Schurs using an affine version of matrix Schubert variety. And then one of those constructions includes the functions on the Centralizer family, which is the K-theoretic analog of which is the title of my talk. So, but most of the time I'm not going to be talking about that. And I'll also talk about how these two things both have these coordinate ring constructions and how Constant made this isomorphism between them. And Peterson gave a different kind of isomorphism, so we'll compare those. So that's sort of the big picture. Okay, so I'm not going to read the slide. I'm just going to say that, okay, on the one side you have quantum cohomology, on the other side you have homology of the affine Grassmannian. Both of them are equivariant for this the maximal torus of this finite dimensional group. So it's just like the diagonal matrices in your GL in type A. And okay, up to dividing, allowing some localizations, you have to divide by some stuff. But the stuff you have to invert on the quantum side is just the quantum parameters. So it's a very, very mild amount of dividing going on. And so it's not really hurting your life any. And then I'm just giving some names here. So Bumsik Kim gave the presentation of quantum cohomology as functions on this on the total lattice, and Ginsburg and Peterson had a construction of the homology of the affine Grassmannian by the functions on the Centralizer family. And Constant gave an isomorphism between these two varieties. Well, I think maybe literally Constant only did it over a particular fiber, but it just works. It just works over the whole family. So I just put Constant's name on it. And Peterson, the way Peterson describes this bijection, this isomorphism, ring isomorphism, also sends Schubert classes to Schubert classes up to division by some quantum parameters. And so what this means is that the quantum and affine homology Schubert structure constants coincide. So you're not losing any information by going to the other side. And the parameterization does look kind of different. So something that looks simple on one side may look not simple on the other side. It's an interesting correspondence. So here's the presentation for the quantum cohomology. So you have this space of lax matrices, so matrices that look like that, where the x's and q's can be just complex numbers. You look at the space of those matrices, and then you also pair them with their eigenvalues of that matrix, or maybe more precisely, the roots of the characteristic polynomial. You take those pairs, that's the type A total lattice, and there's actually an integrable system living on that. And Constant solved that integrable system in all types, not just in type A. And if you just consider the nilpotent parts, like eigenvalue is all 0, the characteristic polynomial 0, then you get the piece called nilpotent leaf. And so if you just write down what I said about the characteristic polynomial has those roots, you just get, so you write down that characteristic polynomial, the coefficients, you call them quantum elementary symmetric functions, polynomials, and then you just set, and then you just declare what I said in the previous slide. You get these equations that have of this ideal IQA, the quantum elementary. The ith quantum elementary must equal the ith elementary evaluated at those A's. The A's are the equivariant parameters for those in the know. And if you just set all the A's to 0, or you just leave them out, then you get just this IQ. And the theorems of Giventhal, Kim, and Kim are that if you make those ideals and mod out these polynomial rings by those ideals, you get a construction of the quantum cohomology rings for flags and the equivariant version. So this is ancient history, I guess. But when I want to emphasize that this construction comes from its functions on some variety. So now we all want to know about how to compute. So we want to know what the Schubert polynomials are for the situation. And I'll first remind you about double Schubert polynomials, but instead this time I'll talk about the left divided difference recurrence. So at the top there I have the formula for the double Schubert polynomial as this product over I and j, xi minus aj. And if you take the divided difference in the a variables instead of the x variables, instead of having a right descent, you get left descent. And you can think that works because of this symmetry between the x and the a. And so now you do the same thing. Okay, so what I did next is I just took the double Schub and I gathered all the product terms with all the aj's together, and then turned that thing into elementary symmetrical polynomials in the first n minus j variables. And then I just swapped out the elementary for a quantum elementary. And that's the formula for the long element, the long quantum double Schub. That's it. And then to get the arbitrary double Schub, quantum double Schub, you just use that divided difference with respect to the a's again. So we're sort of quantizing the x, and then the a's are just working like normal. And so to get between the different quantum Schubs, you don't have to know anything about the quantumness to be able to go between them. And then you set the a's equal to 0, you recover the definition of quantum Schubert polynomial of Bowman, Gelfand, Postnikov. And this definition is due to Kirillov and Maeno and Chiokum, Fontaine, Fulton. And these things represent classes in quantum cohomology of flags and equivariant one. It's surprising how long it took some to bother to write down the details that the double quantum Schubs work. So this is due to Anderson and Chen, and Thomas and I did it independently. Okay, so that's the quantum side, light, airy, not very many details, introduction to the quantum side. Now I'm going to spend a lot of time on the homology of affine Grassmannian side. So it turns out that when I haven't necessarily seen the same amount of evidence of this in usual Schub land, but in many other situations, if you want to understand some polynomials, you need to understand the operators that make the polynomials. And this means like some kind of Hecke algebra, nil Hecke algebra in our setting. And so this is coming into play here. So I'm glad that Liz talked before I did, because she just defined the affine vowel group. So here we have a polynomial ring. The equivariant cohomology points a polynomial ring. You can think in variables a1 through an. Well, we need to set the sum of the a's to be 0 because we're working SL. And then so these just get permuted by the usual vowel group. And the affine vowel group, in this case, the level 0 action, the translation elements just don't do anything. So the translation is like moving from one hexagon to another hexagon. And those don't do anything in this action. So you just use this classical projection from the affine vowel group to the finite vowel group. You just pretend that every hexagon is living at the origin, and then use that finite permutation. And the zeroth reflection acts the same way as the reflection that switches 1 and n. So that's the action of the affine vowel group on polynomials. And we need to allow some denominators just for technical reasons. We have to divide by roots, so that in type A, we have to allow AI minus AJ to be a denominator. And we have to consider this twisted group algebra. So we have permutations, or affine permutations, and these polynomials with maybe some mild denominators. And so we should really think of these as being operators. Everything is going to act on polynomials or quotients of polynomials. We're either going to have permutation operators or multiplication operators. But because if you multiply first and then permute, the permuting will act on the thing you multiplied by. So in this algebra of operators, if you want to commute a permutation operator past the multiplication operator, you have to act on the multiplication polynomial. So that's this twisted group algebra. The vowel group is acting on the polynomials, except that the translations don't. They act by the identity. And so the level 0 affine nil Hecke algebra is the algebra that you get by taking polynomial multiplication by polynomials and good old usual divided difference operators. So this AI is just, identity means take your same polynomial, and then SI means swap AI and AI plus 1, and you have to divide by AI minus AI plus 1. That's the same formula as everyone should know and love by now, except we're also allowed to do this for I equals 0. And in this case, well, what is alpha 0? Well, we have to, small torus, or level 0 means we're forgetting delta. We're setting Liz's delta to 0. And so this means that alpha 0 becomes minus theta, where theta is the high root, or so this is theta is a1 minus an. And s theta is swapping 1 and n. And you can use a twisted Leibniz rule to switch every divide difference operator past every multiplication operator, so that making all the a's go to the right. And when you do, you can see that there's a left S module basis given by just the divide difference operators, so these compositions of divide difference operators. Okay. Now it's not obvious, but because you did this level 0 business, this algebra has a big so the amount of stuff that commutes with scalars is a really big thing. If you have if you allow the full torus action, then this object becomes trivial. But here you get a nice big algebra of things that just all the Peterson subalgebra, all the stuff that commutes with all the polynomials. And Peterson proved that this thing is a commutative algebra over the polynomial ring, and it's isomorphic to equivariant homology, small torus equivariant homology of the affine Grassmannian. And what you should think of is that we know that translation elements commute with all the polynomials, but there are these little divide differences is dividing by some roots. So it's the only mystery is exactly what roots are allowed to divide by. And it took me a while to realize this, but eventually I realized that, there's a lesser known paper of Goretzky, Kottwitz, and McPherson, which basically tell you this. So if you looked in the paper, you wouldn't see the statement. And similarly with Bezer-Kavnikov, Finkelberg, and Mirkovic, they are just looking at this equivalent homology as their presentation. They're just thinking of just a variety, and so their variables are just variables. But if you interpret their variables to be translation elements and roots, then you get this theorem. This is my little value-added version of BFM theorem, that exactly what you get in terms of translations is elements, polynomials, and elements 1 minus translation by alpha check divided by alpha. That's exactly the stuff that you get. And there's a dual way of saying this in small torus equivariant cohomology of the affine Grassmannian, which I realized a long time ago with and had in a paper with Lamb and Schilling, that there's an additional condition to the usual Kosten and Kumar type GCAM condition that you have to add because you're using a small torus. And GCAM also tell you that. That's convenient. Okay, now here's the really cool thing about this situation. You can compute, if you have the fortitude, you can compute everything. So, so let WF minus be the min-length coset representatives in this quotient of the affine vowel group by the finite vowel group. And those are the things that index the Schubert classes. And for every such affine Grassmannian element, there's a unique element to the Peterson algebra of this form. Remember, everything is a linear combination of these divide difference operators. Divide difference operator A sub W occurs once, and then no other A sub V's for V affine Grassmannian occur. All the other terms are not Grassmannian. But if you compute this thing in the A sub whatever basis, then those coefficients are the equivariant Schubert structure constants for the homology of the affine Grassmannian, and hence for the quantum cohomology of finite flags. So if you have the fortitude, you can compute these elements, and you will get all these coefficients. This is an algebra you can really compute things in. Now there's a thing I want to emphasize is this left divides difference action. You should really be, if your life to be easiest, you should be using divide difference with respect to the equivariant variables, which means you should always be working with double. Whenever you should always double, and then you should always do the divide differences in the equivariant variables. It bypasses the difficulties of the structures the new structures you're dealing with. So there's an action of the whole Hecke algebra on this Peterson subalgebra, and S acts by multiplication, translations act by multiplication, and finite permutations act by conjugation. And so they in particular, they act on the polynomial part in the expected way, and they act on the translation weight in the obvious way. And Peterson knows all. Peterson tells you that if you want to compute the J basis element, you can just take the left divide difference element A sub W and act on 1. And I did a sample computation for you in all types for the zeroth guy. You just do the zeroth left divide difference on 1, and you get this expression. Now this expression is written in terms of, it's in T. It's not written in the divide difference basis. But there's a formula for how to go from a simple reflection to the divide difference basis just by rearranging the definition of divide difference. So in principle, you can, well, you know, we've done this in this particular case, but you can just plug in that stuff and expand in the A sub W basis and get all of your structure constants. And moreover, this T, of course, that translation element is an element of the affine vowel group. But to go from elements of the affine vowel group to the A basis, that's exactly just localization. That is the Billy formula. So you could just use Liz's formula because we're in the affine setting to compute that expansion. Oh, so the next thing we want to do is talk about symmetric functions, because this is near and dear to my heart. I like to put things in symmetric functions. And so, well, I read Bott and looked at what he said, and if you just add epsilon to Bott, he says that the homology of the affine Grassmannian of type A is the Hopf isomorphic to the part of symmetric functions generated by h1 through hn minus 1, the first several homogeneous symmetric functions. And then you start thinking to yourself, well, I know there's a Schubert basis, and because this thing is has this dual Hopf, this Schubert basis must have positive structure constants for both multiplication and co-multiplication. And this is just part of symmetric function. You start asking yourself, what kind of miraculous basis could this be? Well, so I heard these talks by Jennifer and company, Jennifer Morse, about K-share functions, and I couldn't understand anything about them until they started showing me pictures of the affine symmetric group, and then I said, oh, okay, I know what to do now. And so then I guessed that these were the homology Schubert basis, and then Thomas. I was just blabbing about at some conference, and Lamb was a graduate student. He was listening, and then he wrote this JAMS paper on this subject. And the funny thing is that at the time I wasn't convinced that this Nilhek algebra was the correct thing to work with, and so he asked me to join with him to do this project, and I just let him do it by himself. So that was like I just lost out on a JAMS paper because I wasn't convinced that this is the right approach. Well, he had already written his paper on affine Stanleys, so I should have trusted him. It was probably good that he got the paper by himself, but you know, one only has a certain number of chances in one's lifetime for elite level papers if you're an ordinary person. Okay, and I'm definitely an ordinary person. So I thought I'd chuck in. So I thought I'd chuck in the definition of the K-shares. So we have the affine symmetric group of these simple reflections. And there's an action of the affine symmetric group on partitions, and the ith reflection acts by adding or removing every remove or addable a corner of residue I. So you label the diagonals, 1, 2, for n equals 3, 0, 1, 2, 0, 1, 2, 0, 1, 2, like that, and you do this, and if you look at the orbit of the empty partition, you get exactly n cores. And of course, because exactly the zero reflection is what you're allowed to do when you have the empty partition, the stabilizer of the empty partition is the finite symmetric group, and therefore these cores are in bijection with affine Grassmannian elements. And we'll just say core of W for the core corresponding to the affine Grassmannian element W. And okay, so you can make a partial order out of this, the left weak partial order, and then you can just define a horizontal weak strip, which is Lapointe-Morse definition, that you want your definition of the difference of lengths of the vowel group elements to be R, and you look at the corresponding cores. They have their skew diagram forms a horizontal strip in the usual sense, at most one box per column. And so the theorem is that there's a unique basis indexed by partitions, and they're called K-Schur functions, a basis of the part of the polynomial ring of symmetric functions generated by h1 through hn minus 1, such that the empty core, the empty partition is equal to 1. That basis element is equal to 1. And then you have this, and then you know how to multiply by these H generators. And multiply them by one of these H's is just adding horizontal weak strips in all possible ways. So that is the definition due to LaPointe and Morse, and just as added color, you can also that's actually a definition by dual, like the H's are dual to certain M's, and then this gives you a monomial expansion of the dual basis of dual K-Schur functions. The K-Schur functions themselves have a strong tableau generating function, but that I'm not going to talk about. And a deeper fact is that the K-Schur functions are Schur positive. So we have a really complicated proof back in the day, and then they have a much more brilliant, more useful formulation of the coefficients due to Blazek, Morse, Punt, and Summers. Or recently, which is part of an amazing bunch of papers they've been doing. And just to be clear, these K-Schurs that they do come with a parameter t. We're saying that t equal to 1. Okay, I just want to show you some pictures. For n equals 3, all the K-Schur functions are products. This is not true in general, but I just want to show you that there are all these products as little Schur functions in this case. They're nice little friendly things, but their existence is just amazing. The fact that such a base exists is just crazy. Okay, but now I said that I have to double everything. So let's double do double K-Schur, or K double Schur. I haven't decided how to order all the adjectives. So the right way to do things is to have infinitely many A's, and then to forget the finitely many A's in this sort of wrapping the integers around the affine Dickin diagram. So you forget from that one polynomial ring to the other, and then we have to take symmetric functions, but we have to allow the degree to go to infinity. So we take unbounded symmetric series. So that's what that hat on the symmetric functions means. The hat means I allow the degrees to keep climbing. And we have these polynomial coefficients. So that's our usual sort of double variables. And I'm going to use this abbreviation for some series, this Cauchy kernel. We have this generating function for the H's and a generating function for the E's, which is the reciprocal of the other one. And this Cauchy kernel kind of has this exponential-like, looks like exponentials. Has this kind of notation. And so this is something I just realized very recently because of that. When I finally understood what I could do with the BFM presentation, like we didn't have a very good way of saying what this ring was. But in symmetric functions, you can take inside that big, gigantic, too big completion, you can just take the subring generated by these particular series, 1 minus this Cauchy kernel thing divided by that AI minus AJ. And you might think, well, it's kind of bogus divided by AI minus AJ. What the heck is that? But you see, actually, when you expand that in symmetric functions, that's actually a positive. It's actually got no denominators. But the proof is you just isomorph with the BFM presentation. You just send a translation element to a certain Cauchy series, and then you can just, and then it's it's just like changing notation. Like, I was talking sort of recently about this with Takeshi, and he was saying, like, this is becoming clearer and clearer, almost obvious. So, and back in the day when we first were studying this stuff, we have a very difficult construction and very difficult proof of everything. It's so difficult, I think we scared off people from working on it. And I'm hoping that people will want to work on it, on this stuff, rather than scare them off. But sorry if you tried to read some of those papers back in that time. So how can you get at the Schubert basis in general? How can you get the Schubert basis in symmetric functions? Well, you just transport that same stuff in the Peterson algebra over to the symmetric series. You just transport the star action of A on the Peterson. You just replace the Peterson by a symmetric function and do the same thing. And so you just do it. But we didn't find them this way. We found them a different way. But then, hindsight is always clearer. Then you just realize, well, I could have just done that. I could have just isomorphed this other thing. So if you write it down, and the AI for I non-zero is the usual ones, completely usual ones. For the zero, you need to have this translation element, and that translation corresponds to these infinite series. So that zero thing is sticking on this series stuff for you. So as I said, me and Thomas had this bad old definition, and then but the new definition, it just looks like the one in the Peterson. You just take the left divide differences and act on one. And here's the tasty example. You do the first non-trivial example. You put delta 0 on 1, and you get this series. What does it look like? Sure 1 box plus A1 times sure 2 sideways boxes minus A0 times 2 vertical boxes plus so-and-so, with everything being a hook shape. And when you set the A's to 0, you get just the sure of 1 box, which is the K-sure function for that 1 box core. So what you're getting, this is graded, and the degree in the symmetric function has to be subtracted the degree in the A's, and that difference is going to be constant. So you have the equivalent stuff causes stuff to grow up in degrees to infinity, but it acts like it should. You forget, and you get exactly what you want. And for small data, for small W's, you get the basis for the infinite Grassmannian, which are called Molov dual Schur functions. But Molov didn't know what the Schubert calculus meaning of the things he invented, but I realized what they were after I saw them. Yeah. So you can recover K-sures in this. And you might think this is a horrible way to recover them, but it's there are some technical difficulties because it's infinite, but we have this explicit way of getting at Schubert classes. Okay. So here's the promised thing I said I would chuck in. So and this comes with some embarrassing admissions. So in an old paper of Lustig, he tells you how to explicitly make Schubert varieties in the affine Grassmannian of type A. He presents this lattice construction of the affine Grassmannian, and the only thing I want to take from it is that a Schubert variety in the affine Grassmannian of type A is just a usual Schubert variety and a usual Grassmannian indexed by an n-core, but you have to do something that, and then here's the difficult part. You have to intersect with this closed thing, and it's a nasty closed thing. It's this locus fixed by a certain unipotent, and this nastiness is not transverse to anything you want it to be. So you can't do any trivial kind of cheap trick and 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 get around it. You have to do real work. Um, and but I perhaps unwisely sicked a student on it, and but he found uh, set theoretic equations for these things, and have a conjecture that his equations are scheme theoretic. Um, and of course, we played the Knudsen-Miller game. We duly degenerated, Grobny degenerated, and found all kinds of things, none of which we could prove. Um, so, among the things we found were that, and this is sort of a thing that had to happen in some sense, that you take the multi-degree, and after Poincare duality, which you have to do because these are really homology classes, is omega of a K-Schur function. Omega means sort of transpose all your Schur functions. So not sure why the omega is being chucked in there, but and another issue with taking this Grobner way of doing things is that the K-Schurs are defined by a Pierre rule, and I don't know how to incorporate that multiplication information into this Grobner world. So any kind of direct kind of proving that's correct, I don't see how to do that part of it. We stared at the Grobner basis. We couldn't figure out a general formula for what it was, but that could just because we're not clever enough. Admittedly, I didn't try as hard as I could have. So Corey called the corresponding monomia, these ideal little pieces. He called them punch cards. Like you have the matrix in which which of the things are zeros. You punch them. So the analog of RC graph comes from the Grobner degeneration of usual matrix Schubert varieties. They're closed under Schut moves, and I think we basically proved this. And so what this tells you is you get a sum of truncated Stanley polynomials. So such a formula would be a new formula for K-Schurs. And it also proved K-Schur positivity. Now, sadly, well, or maybe not sadly, Blasiak, Morse and company have another way of already getting the Schur positivity of K-Schurs, and so. But the embarrassing thing is I should have written a paper on this, 10 years ago, and I've just been too lazy, or maybe I'm just too embarrassed to not know how to do anything. Yes? So Stanley is when you take a Schubert polynomial and you symmetrize it, or there's appropriate kind of symmetrization. You can take you can just put a bunch of fixed points in front of your permutation and just take that limit, yeah. Or you can apply a isobaric divide different symmetrizer. So there's such a formula. The punch cards are telling us that there's a formula like this, but we couldn't figure out what that was. And one thing that we didn't really do is that, like Knudsen-Miller tell you to look at the torus acting on both the rows and the columns. We only looked at one of the tori. In fact, the less obvious one got us the K-Schurs, but the other one gives you the equivariance, small torus equivariance, and we never bothered studying that, and we should have, but we never looked at that. So the conjecture, meta conjecture would be that or just very vague conjecture. You might get some kind of variant of K double Schur, but here another thing that's tricky is you have to do the Poincare duality, which I was confused about how to do that equivariantly. But anyway, I promised to stick in this Grobner degeneration slide just because I felt like I felt like I had to. So okay, yeah. So here's the last construction of the homology is that in a lot of generality, if you take a principal nilpotent of your Lie algebra, sort of the dual group, and you take its centralizer and take functions on that, you get this Hopf isomorphism with homology of the affine Grassmannian, this Ginsburg-Peterson theorem. And so let's just say what it is for GL. So your principal nilpotent is just that that thing with the ones just above the diagonal, and you take its centralizer, and I'm taking the centralizer in PGL, because otherwise I'd have to have some roots of unity on the diagonal. I prefer to avoid those other connected components. So I'll just work in PGL so that I've scaled that away so there's just ones there. But you just have these bands, and I cleverly call the first band H1, those variables H1, the next one's H2 and H3. And if you call them those things, then you get a Hopf isomorphism. There's a natural Hopf structure on those functions on matrices, and it induces one in the centralizer, and it agrees with the Hopf structure on symmetric functions. So this is the cheap observation I made, and back on the quantum homology side, on the total lattice side, the people that work in integrable systems have these things called tau functions, and the tau functions were written down by Constant. There are these upper right minors, and if you look at what they are in my H notation, you just get some rectangular Schur functions, and we'll also define this tau I prime to be the rectangular Schur function with the corner box punched out. And so Constant tells you that there's this isomorphism from the nilpotent leaf of the toda with the nilpotent with just the centralizer of just the nilpotent with the loc. It works over in open sets. But the brilliant thing is that, well, me and Thomas just went through the exercise of writing down exactly what this means in variables and on the symmetric function side, which admittedly other people weren't looking at. And so we just wrote down where do the variables go. So you get these quotients of Schur functions. That's what you get. And so you can just write it down. So me and Thomas did this amusing exercise back in the day. And so it goes from K Schurs, quantum Schubs go to K Schurs, up to dividing by some of those quantum parameters. That was kind of a fun thing to do. So now you have to double it. So what you do geometrically, I just skip all the fine print, and what you do is instead of just taking your principal nilpotent, you pollute the diagonal with arbitrary junk, A1, A2, and A3. And of course, you cleverly call it A1, A2, and A3, and you think of those as being equivariant variables, and that's the way you should think. And you look, instead of just the stuff that centralizes the principal nilpotent, you take all of these guys and the corresponding matrices that commute with them, the pairs of these kind of things and the things that centralize them, and take functions on that. And then you get the theorem, the equivariant version of the theorem. These centralizer families, their functions are the small torus equivariant homology, the affine Grassmannian. That's due to Ginzburg and Peterson. And then the fun thing you can do is you can ask yourself, well, I've got these matrix entry functions. What do they mean in terms of Schubert classes? Equivariantly, and then this becomes a more difficult exercise than that cheap trick of just sticking H's in those bands and just everything just happens to work. You have to do a little more work here, but if you just write down, okay, I know that this other thing is upper, this E minus E plus H is upper triangular. The centralizer is going to be something upper triangular. Okay, I just write down the commutation. I get these equations. That equation is saying you can solve for any matrix entry in terms of entries that are closer to the diagonal, and so you can solve for everything in terms of diagonal elements. And then the isomorphism, you just send the diagonal matrix entry to a particular translation element. That's it. That's the isomorphism. With the Peterson version. Okay. Yes. So what are those matrix entries? So it turns out that to figure out what they are, you have to go extended. So so you can't stay in the affine vowel group. You have to go into the extended affine vowel group. And so this corresponds to working in the affine Grassmannian of PGL instead of the affine Grassmannian of SL. So you're working the adjoint group instead of the simply connected one. And it just means you'll just have, instead of having one copy of the affine Grassmannian, you sort of have several sheets, and they sort of, they're sort of, so you don't really get truly more complicated stuff, but it's needed in this situation. So you have this extended version of the Peterson theory, just adding this little, and the amount of extra stuff you just had is this group of rotations of the Dinkin diagram. That's the extra stuff you get. And what we computed is that a matrix entry is given by this ratio of Schubert classes, equivariant Schubert classes. But the guy on the bottom is that guy on the bottom is just a single translation for fundamental weight. The thing on the top is a little tastier. It's like a row class, but with this little twist in it. Yeah, and you can't. It's very difficult to express this answer without using the extended affine vowel group. In fact, I wrote a whole bunch of junk with symmetric functions, like trying to say what it was, and then after I realized that you could do this, I just deleted all that stuff, and now I wish I'd remembered that stuff because I want to know what those symmetric functions are now that I'm doing type C with Takeshi. But yeah, so but yeah, you really need the extended to see the Schubert classes here. So this is sort of a fun thing to do. Okay, so in K theory, conjecturally you can do all the same kind of stuff. So a couple years ago, Thomas, Changxing Li, Leo Mahalsia, and I had this conjecture that quantum equals affine in K theory, and the important thing is a finite dimensional Schubert writing the affine Grassmannian, the structure sheet for finite dimensional, and that was not the basis that some people were trying to use on that side of things. It's apparently been proven by Shukato, but as you can see, it has 7 versions of his paper on the archive over the past, going from 2018 till last year. There's 7 versions. I'm not sure if that paper has been accepted by the journal or not. But some of his co-authors assure me that the formulas are correct. But they're not sure about the proofs, but the formulas are working. So no, I think they computationally they know the correct. Yeah. Naito told me this. I asked him like a couple months ago. What's the status? Yeah. No, I mean, I've talked to Shu, but like I don't understand stuff. I didn't understand his explanations. So anyway, so I'm just reminding you of this big picture at the beginning in homology and cohomology, and so that arrow at the bottom, the Ginzburg-Peterson arrow, was known non-equivariantly a couple years ago by Ikeda, Iwao, and Maeno. And so the new theorem I'm announcing is that we have the equivariant analog of that. So we have the equivariant K theory of the K-homology, the affine Grassmannian, localized. This is the same thing as equivariant quantum cohomology, K theory of the finite of usual flags, localized. I'm sorry, that's not right. The centralizer family. So we only know the bottom arrow. So and I want to give credit to Kirillov and Maeno, who conjectured at some point the connection with quantum cohomology. Although if you believe the Kato isomorphism, then that would follow from this other thing. But all of the other parts of this, picture, the direct. I guess I guess Kato does claim to have proved this Peterson isomorphism in K theory, in some, but I don't know of any general replacement for the Kim and the Giventhal-Kim presentation, nor this Costin isomorphism. I don't know of any general statements like that in K theory, so that would be interesting to know, and that's part of the stuff I want to work on. But here's the thing that we did, and we just to make the equation look right, I had to pollute some stuff with these exponentials and a's, but you get your centralized equations get you the same recurrences as for the appropriate Schubert classes in this on the affine Grassmannian. So stuff kind of works, and also the tau functions, these upper right minors have these miraculously good properties also. Yeah, so there's a lot of things to work on. So all those parts of the big picture that we didn't know how to do. Yeah, lots of stuff to work on, especially like these even symmetric function bases. Like here's the embarrassing thing. Like for the small torus equivalent cohomology of the affine Grassmannian, that's just like take dual case sure and double. We know no good formula for this, like no good combinatorial formula. That's kind of embarrassing. Like it's like I don't know how to write down an affine Grassmannian double Schub. Most of the stuff I was talking about so far were homological things, are dual to them. But yes, but that's just it's just tastier. You just have these pairs of things you can work with that are not isomorphic; they're dual. And it's fun to work with classical groups. Like I'm having great fun in Type C with Takeshi because he's sort of a P and Q function expert, and I did my thesis on multiply Q functions, so I'm supposed to be expert, but I'm not really. And so I'm learning all this stuff about how to equivariantly deform these Q functions, and we're doing all that fun stuff. Yeah, and yeah. So in terms of combinatorics, just any kind of double combinatorics, there's almost nothing known, just almost nothing known. So I'm hoping that people will want to do a little bit, fill some of these kind of embarrassing voids. Anyway, that's